This is our first video of the year on Chapter 1, Lessons 1 and 2 for AP Stats. So the idea with these videos is I try to guide you through some examples to get a general idea of exploring the concept before we dive into more problems in class. So our guiding question here is, what are the different types of variables, data, and distributions we can use to learn more about a data set? Or about something in general. What is involved in each of these? So this outline, the student copy of it will be available online, so feel free to download that from Schoology. And I'm going to touch on the biggest, most important parts of this in the video, and then we'll discuss the rest in class. Ideally, you should watch the video, then read over the lessons in your book. There's nice little summaries at the end of each lesson that are really sum things up well. And then answer the multiple choice, which is in the video here, and a free response question about the video and the topic. So a distribution, when we say the word distribution, it tells us what values the variable takes on. Those would be on our x-axis, if we have a histogram, and how often they take on those values. So dot plots, stem plots, histograms, box plots are all types of ways we'll look at displaying a data set. And going beyond our data to make inferences, for example, to get a random sample from a population and then be able to generalize the results of that to the population are key goals in statistics. So we're going to look at some of your data today from how long is a minute, your estimates of how long a minute is, in order to look at what we can learn from that data. Before we do that, we're going to look at types of data. Categorical data, bar graphs are generally good ways to do that. For example, if we wanted to see the distribution of colors of cars in the parking lot at the cathedral. Color is a category, it's not a number, numerical value, so that would be categorical data. So consider what the data you will have and what type of distribution, what type of visualization would be the best way to see that. One of the least objective ways to display data is a pictograph, such as the one you see above, because they don't tend to accurately represent the quantities that we see, especially because oftentimes we represent quantities by the vertical distance, so a bar graph, how tall the bar is to show us the quantity. However, a pictograph is in 2 dimensions, going up and to the side, so this box is much larger than the rest. Two-way tables are a key way of organizing our data and looking at 2 variables. For example, here we have gender and choice of superpower. So a two-way table implies there's two variables being measured. Now, we have 2 types of distributions we can gather from it. We can look at the total columns, which we would only do that if we wanted to have a question about one variable. So invisibility, super strength, like choice of superpower. We could say 30 out of 200 or 15% chose invisibility. On the other hand, we could also look at gender. So we could say 115 out of 200 or 57.5% of the 200 people were female. That would be a marginal distribution. Marginal is just going to look, and because of that, we're only going to use the total column. So marginal distribution of superpower, we would just use the totals for superpower, and then my denominator for all those would be the total people asked. Marginal distribution of gender, I would look at the 115 over 200 and 85 over 200 for gender, and then the total column would be my denominator. A conditional distribution would use the values in here, and they could let us know things like, does the value of one variable affect another? So does being female affect your choice of superpower? Does your gender affect your probability that you'd like telepathy or invisibility or super strength? So conditional distribution, we're always looking at 2 variables, and for that reason our value for our numerator is always going to come within the table, not in the total column, and our value outside would come from the total columns down here, not the lower right total asked. Now this is a good one to go ahead and review, because this is a common mistake as far as confusing the 2 and how to calculate them. So here we have a marginal distribution described by the table. Here we have it broken down by percents. To describe 15% of females chose invisibility, 15% of males chose invisibility, 3% of females chose super strength, or approximately 3. 20% of males chose that. Big difference sticks out there. So conditional distribution, it's among individuals who have a specific value of another variable. So this is breaking it down by gender. So the value of the second variable would be gender, and looking at choice of superpower based on that. That's a conditional distribution, always looking at the values of a variable given values of a second variable in the table. So to decide how to use your data, always think about what the explanatory variable is and the response variable. Now, you may in science classes and other math classes heard the explanatory variable referred to as the independent variable. Independent has a very different meaning in statistics as far as affecting probabilities. So we don't use the word independent variable. Explanatory variable is a much better term to use in this case because it's explaining the response. It's the cause. The response variable is the response to that explanatory variable, also called the dependent variable oftentimes. So we will not use those words because independence has a different definition. Independence means values of one variable do not affect values of a second. When we organize problems this year, we're going to look at state, plan, do, conclude. One way you can remember this is statistics problems demand consistency. That's one the book offers. Not my favorite, but if it helps you, cool. If you think of a better one, please let me know. So we're going to organize by stating our problem, planning, checking conditions, and deciding which method, which calculations we need to do, carrying out our calculations, and then concluding by explaining what our calculations mean. Now, this explanation of our problem may be something that's newer to many math students because perhaps before you're just given a problem, 2x cubed when x is 3, what does that equal? And then you move on. Really what we're looking for is the ability to apply this to something useful in the real world. So we want to be able to conclude and explain what our calculations mean in terms of a problem. That's why I like statistics, because it's applicable. Now to quickly jump to our box plots. We're looking at block 3 here and block 4. One problem I ran into when I took screenshots of these were that the range was different. So I tried to change the pictures to make the axes line up. Couldn't quite do that. What you can see is that the spread of block 4 is much smaller, meaning people were closer to the median. So here's my minimum. If it's an outlier, meaning far enough from most of the data, it's a dot. So we have an outlier above and below in block 4. In block 3, we just have this outlier way above. When there is no outlier below, so this would be my minimum, my smallest. This would be the first quarter of my data is less than this number. My median is right here by the middle line. My third quartile, meaning 3/4 or 75% of the data is less, is up here. And then my maximum that's not an outlier is up here. So that's a box plot. Let's take a look at what that looks like in terms of a stem plot. Here's just a quick explanation of one way we would show that an outlier being up here. We call these whiskers, the minimum, the maximum that aren't outliers. We'll talk about how to define an outlier in class. And then you can look at where the mean is. The box plot's a nice way to do this because it gives us sometimes the median can be a better measure of center. It's not as affected by an outlier as the mean is. So here are stem plots for block 3 and block 4. Notice that the value here is the number in the tens column. So 8 and 1 refers to somebody's guess was 81 seconds. 8 and 4 refers to 84 seconds. So this can give us a nice spread. Try tilting your head clockwise 90 degrees, so you're sideways, and that's what a histogram would look like. Histogram is similar to a bar graph, but it's for quantitative values, and there's no gaps in between the bars. Now we can split the stems, and what that would mean is that I'd put 30 to 34 on one line and 35 to 39 on the next line. Let's look at what these same graphs look like with split stems. So here we are with split stems. 30 through, somebody had a guess of 30 here. 30, 0 through 4, and then you go 5 through 9. 40 through 44, 45 through 49. 50 through 54, 55 through 59. So it's a way of spreading it out and making the stem plot a little more useful. You can detect more categories like where my peak is. You can quickly see my mode for block 4 was 54 because it appears 3 times there. So you have to look at your data and see how spread out it is. If it's clumped together, it's often good to use a split stems, meaning you separate the ones values of your data from 0 to 4, then 5 to 9, and so on. So this is a split stems on my stem and leaf plot. Here is your multiple choice question, referring back to marginal and conditional distributions. So a two-way table is a table with blank, the number of variables, and can be used to calculate blank, marginal distributions and marginal distributions but not. So pause right here, read over 1.1 in the summary, and answer your multiple choice. Then push play. I'm going to quickly explain a little bit of 1.2, and then your free response question will pop up. So please pause now, look over Chapter 1, Lesson 1, especially the summary, and look over any terms if you're confused in the vocabulary. We've already covered a good chunk of 1.2 because they have a lot to do with each other, so dot plots and stem plots and histograms. And what are the four aspects of a distribution we describe in order to learn more about it. So dot plots, each data value is a dot above its location on the number line. So you'd have like an x-axis with dots above it. The y-axis would be counts, how often each value appeared. We just looked at stem plots in the example from earlier. Here's an example of back-to-back stem plots. If we're comparing two sets of data, you can have one go from 0 be closest to the stem, the leaves go in numerical order to the left, from right to left on our first data set and from left to right here, so we can compare these two data sets. If you'd like to look more at this, please pause and take a look over it or look at it in the outline. We're going to move on to histogram. So histogram is very similar to a dot plot except for the dots become a big bar. Now it may look like a bar graph, however remember a bar graph is for a categorical variable, not a quantitative variable. This is a quantitative variable we'd be using, heights of black trees, cherry trees. We call each of these bars a bin. Notice the bars are next to each other. A bar graph would not have that quality. This can give us a good idea. To look at this, we want to look at socks, or shape, meaning the mode. That appears to be right here. Most values occur between 75 and 80. Now notice this is inclusive of 75, so values greater than or equal to 75 but less than 80. So that's my mode. That'd be my shape. Outliers. Right now we can just look at it and we're going to say visually it does not appear like there are any outliers. We're going to define them in class. Center. It appears to be centered. You know, we have a lot of our data here. It's pretty symmetrical. So the center appears to be right around here, right close to 75, probably maybe a little above because we got more values up here. So we're going to talk about center. When we have skew or a big tail on our distribution, we want to use the median. When we look pretty symmetrical, the mean and the median will be about equal, so we can use the mean. So that's shape, outlier, center, and then finally spread. So range, the range here is from 90 minus 60, or range is 30. So my maximum minus my minimum. IQR, the interquartile range, and standard deviation will be two other measures of spread we'll use depending on skew. If we have a skewed distribution, we're going to use IQR, and if we have a symmetrical distribution, we'll use the standard deviation. So here's a quick breakdown of what I just said. Shape, you're looking for the peak, the mode, what a value occurs the most. Skewed right would mean a tail to the right of the distribution. So values that are far to the right or bigger than most of the data set, where most of the data is. Skewed left, you'd see a tail to the left, meaning you have some values far to the left away from the rest of the data set. Skewed right, it's called right because it pulls the mean up or to the right. Skewed left, those values would pull the mean down. We can use the median always as a measure of center. The mean makes a lot of sense when it's symmetric, and we'll talk about why we'd want to use the mean when it's symmetric as we go on. Like mirror versions, as if you put a mirror down the middle. Spread, we're going to look at the range. We can also look at the IQR and the standard deviation. So we use the IQR when skewed. We use standard deviation when symmetrical. Outliers fall outside the overall pattern of the graph. We'll talk about the definition of outliers soon. Here's an approximately symmetric distribution. Notice you could put a mirror right down there. The left looks like the right. Skewed right, if you drew a curve over this and cutting off, you'd have a tail over to the right. This value is pulling the mean up far more than the rest of them, having more of an effect. So outliers are having an effect on the average, but not the median. And we'll talk about why. Skewed left, you'll have that tail to the left. These values are pulling the mean down. Unimodal, one mode, one peak. Bimodal, two modes, two peaks. Multimodal, three or more. Here is your free response question. I want you to comment on the shape, outliers, center, and spread. Just give a visual estimate of outliers.